Good morning, everyone. Respected teachers, mentors, and my dear friends. It's my pleasure to present our internship project titled EV ADAS System, Real Time EV Dashboard, and ADAS Warning System. This project was developed during our Automotive Embedded Systems internship. During the internship, we gained practical knowledge of embedded systems and their applications in modern electric vehicles. We learned how embedded controllers communicate with sensors, process real time information, and assist drivers by improving safety and efficiency. Throughout the internship, we worked with the STM32F103C8T6 Blue Pill microcontroller, STM32Cube IDE, Pixim Lab simulation software, and Python for dashboard development. We also learned various embedded programming concepts such as GPIO configuration, analog to digital conversion, timers, PWM generation, UART communication, interrupts, ultrasonic sensor interfacing, state machines, faulting management, and real time data visualization. The knowledge we gained helped us understand how intelligent automotive systems are designed and implemented. Today's presentation is divided into different sections. Today, first I will introduce the internship and explain the objectives and system architecture. After that, Karthik Gupta will explain the implementation, followed by Vibhav Sharma discussing testing and results. Finally, then a project will be introduced by Gaurav Sharma, with which will conclude with the live demonstration and future scope. Our internship our internship was conducted over a period of 14 days, with which each day focusing on a different aspects of embedded system development. Initially, we studied the fundamentals of automatic embedded systems and importance of advanced driver assistance systems, commonly known as ADAS. After understanding the theoretical concepts, we moved to the practical implementation using the STM32 Blue Pill microcontroller. We learned GPIO programming tool interface LED and switches, ADC for reading and analog sensor values, timers for accurate timing operations, interrupts for real time event handling, and PWM generation for motor control. Later, we implemented UART communication for transferring data between STM32 microcontroller and a computer. We also learned ultrasonic sensor interfacing, which is one of the most commonly used sensor in obstacle detection. Towards the end of the internship, we integrated all these modules together to build an EV controller capable of monitoring vehicle parameters, detecting obstacles, and managing faults and displaying all information on a Python based dashboard. This gradual learning process allowed us to understand how individual embedded modules work together to create a complete automotive application. Modern electric vehicles requires continuous monitoring of several important parameters such as battery condition, motor temperature, vehicle speed, and surrounding obstacles. These parameters are essential because they directly affect vehicle performance, battery life, and passenger safety. Most modern vehicles include advanced driver assistance systems that continuously monitor the surroundings and warn the driver about possible collisions and dangerous situations. However, commercial ADAS systems are expensive because they are high-end sensors such as radar, lidar, and multiple cameras along with powerful processors. Such systems are generally available only in premium vehicles. Our objective was to design a low-cost educational prototype that demonstrates the basic working principles of EV monitoring system and ADAS using affordable hardware. Instead of expensive sensors, we use ultrasonic sensors for obstacle detection, the STM32 Blue Pill microcontroller for processing, and Pixim Lab for simulation. This approach makes the project suitable for learning, research, and academic demonstration, while still implementing the fundamental concepts of ADAS. The main objective of our project was to develop an embedded system capable of monitoring important vehicle parameters in real life. The first objective was to monitor battery state of charge, motor temperature, and vehicle speed continuously. The second objective was to estimate the remaining driving range based on battery condition. The third objective was to detect nearby obstacles using ultrasonic sensors and generate timely collision warning to improve driver safety. Another objective was to implement blind spot detection and parking assistance features for using distance measurements. We also designed a fault management system capable of detecting abnormal conditions such as sensor failures and unsafe operating states. Finally, we developed a Python dashboard that receives all the vehicle information through UART communication and displays it graphically in real time. Before implementing the project on actual hardware, we stimulated Pixim Lab, which helped us verify the firmware and identify possible errors before deployment. Overall, our goal was to integrate sensing, processing, communication, and visualization into one complete embedded automotive application. The slide shows the complete architecture of our ADAS system. The system starts with different input sensors. The accelerator pedal provides the throttle input, which the brake pedal provides braking information. The battery monitoring circuit continuously measures the battery state of charge, and the motor temperature sensor monitors the health of the electric vehicle. Ultrasonic sensors placed around the vehicle continuously measure the distance to nearby obstacles. All these sensor values are sent to the STM32 Blue Pill microcontroller. Inside the controller, the EV control module calculates vehicle speed, battery status, and other parameters. At the same time, the ADAS engine processes the ultrasonic sensor data to identify nearby obstacles and determine whether any warning should be generated. The process information is then forwarded to the fault manager, which checks for unsafe conditions and activates the appropriate warnings messages whenever necessary. Finally, all the process data is transmitted through UART communication to the Python dashboard. The dashboard displays battery percentage, speed, obstacle distance, warning indicators, and all other important vehicle parameters in real time. The modular architecture demonstrates how different embedded software components interact to build a complete automotive application. With the with this overview of our project, I would like now to invite the Karthik Gupta, who will explain the technical implementation and working of the system in detail. Thank you.
Good morning, everyone. My name is Karthik Gupta, and today I am going to present my project on Advanced Driver Assistance System or ADAS using the STM32 microcontroller and HCSR04 ultrasonic sensor. The main objective of this project is to develop a real time obstacle detection system that measures the distance of nearby objects and displays the information on Python dashboard. This system combines embedded systems, sensors interfacing, serial communication, and software visualization. Now, I begin with my slide. The slide explains the overall objective and technical architecture of my project. The project is divided into four main layers. The first layer is sensor layer. Here, I interfaced the HCSR04 ultrasonic sensor with the STM32 microcontroller. The sensor sends an ultrasonic pulse, and when the pulse reflects from an obstacle, it returns and echoes. Using the STM32 timer, the echo time is measured accurately, and this time is converted into the distance of the object. The second layer of this processing layer, in this stage the firmware calculates the distance from the echo time using the speed of sound. It then compares the measured distance with the predefined threshold values and classifies the situation into safe or warning conditions. The third layer is the communication layer. After processing, the STM32 sends the distance value of the computer using UART, which is an serial communication protocol. UART files data through transmit and receive pins, making communication simple and reliable. The final layer of the dashboard layer. A Python application receives the serial data, processes it, and displays the live distance value and warning indicators. This allows users to monitor the system in real time. Now, the core of the project is the STM32F103C86, also known as the Blue Pill Development Board. It acts as the brain of the system by reading sensor data, processing it, and controlling communication. For firmware development, I used STM32 Cube IDE along with HAL or hardware abstraction layer. HAL simplifies programming by providing ready-made functions for peripherals like GPIO timers and UART. The objective, I used the HC SR04 ultrasonic sensor which can measure distance ranging from approximately 2 cm to 4 meter was good accuracy. For communication between the STM32 and the computer, I used UART at baud rate of 1,15,200 bits per second. This allows the major data to be transmitted continuously. Before implementing everything on hardware, I used PixSimLab to simulate the circuit and verify the firmware. Finally, I developed a Python dashboard using serial communication libraries. The dashboard receives the transmitted data and displays live distance measurements along with warnings, making the system easy to monitor. The slide shown how I completed this project over a period of 14 days. During the first 4 days, I learned the basics of STM32 controllers, including GPIO programming, timer configuration, and STM32 Cube IDE development environment. From day 5 to day 8, I integrated the HC-SR04 sensor with the STM32 and implemented accurate distance measurement by calculating the echo pulse duration. Between day 9 and day 11, I focused on UART communication from STM32 to a computer and verified successful communication. Finally, the day 12 to day 14, I developed the Python dashboard, tested the complete system, and fixed any communication or display issues.
So good morning everyone, I'm Raghu Sharma and I'm going to talk about these ADA systems. So here in this slide, we'll talk about the layered firmware design. So this slide explains the layered firmware architecture used in the ADA system. The firmware is divided into three layers, which is hardware abstraction layer (HL), and the control and the ADA logic. The hardware layer contains the STM32 microcontroller, sensors, and actuators. The HL acts as an interface between hardware and software, simplifying communications through drivers such as GPIO, ADC, UART, and timers. So the top layer contains the application logic responsible for obstacle reduction, speed calculation, and decision making. This layer approach improves modularity, debugging, maintenance, and scalability, allowing developers to modify one layer without significantly affecting the others. So talking about the STM32 Blue Pill overview. So in this slide, which introduces the STM32 Blue Pill development board, this serves as the central controller of the ADI system. It is based on the STM32 F103C8T6 microcontroller featuring a 72 MHz ARM Cortex M3 processor, 64 kilobyte flash memory, and 20 kilobyte SRAM. So the controller processes data received from sensors, performs calculations, and controls outputs such as LEDs and warning systems. It includes built-in peripherals like ADC, GPIO, UART, I2C, SPI, and timers, enabling communications with different hardware devices. Due to its high performance, low cost, and low power consumption, the HTML2 Bluepill is widely used in embedded systems. Now, talking about the next slide, we have the digital input output section, GPIO, and LED control. This slide explains the role of GPIO, general purpose input output, in controlling digital devices such as LEDs and push buttons. GPIO abstraction allows developers to control hardware using simple software functions instead of directly accessing hardware registers, and LEDs indicates different system states while buttons provide user inputs. The firmware initializes GPIO pins, configures them as inputs or outputs, and control their operation effectively. Debouncing techniques removes false button presses caused by mechanical bouncing. This abstraction improves code readability, portability, and reliability while ensuring accurate communication between the microcontroller and connected hardware components. Talking about the next slide, we have the ADC and analog sensors. This slide describes how the STM32's 12-bit analog to digital converter ADC converts analog sensor signals into digital values for processing. The sensors such as throttle position and battery voltage produce analog outputs that cannot be directly processed by microcontrollers. The ADC converts these signals into 4096 digital levels for accurate measurements. DMA, direct memory access, enables continuous data transfer without increasing CPU workload. A moving average filter removes electrical noise while the runtime calibration improves measurement accuracy. Finally, the processed values are converted into engineering units, enabling precise monitoring of vehicle performance and battery conditions. Talking about the next slide, we have the HCSR04 ultrasonic sensor drivers. This slide explains how the HCSR04 ultrasonic sensors measures the distance to nearby objects. The STM32 sends a 10 microsecond trigger pulse, causing the sensor to emit ultrasonic waves. These waves reflect from an obstacle and return as an echo. The microcontroller measures the echo pulse duration using hardware timers and calculates the distance using the formula distance is equals to time echo divided by 58. Uh, the firmware validates the measured value to eliminate invalid readings and timeout errors. This sensor is widely used for obstacle detection, collision warnings, and parking distance in the ADA system. The next slide, we have a timers, PWM, and cooperative schedulers. This slide explains the use of timers, PWM, and the cooperative schedulers in the ADA system. A timer 2 generates a 20 kilohertz PWM signal to control monitor speed by adjusting the duty cycle according to throttle input. That time in session protects motor drive circuits from short circuits. Timer 3 produces a 1 millisecond system tick that drives the cooperative scheduler. Tasks such as sensor reading, motor control, and display updates execute at fixed intervals without interrupting one another. This scheduling method is simple, efficient, predictable, and ideal for real-time embedded system with limited resources. The last slide, we have EV controller modules. This slide describes the EV controller module, which manages vehicle performance and battery energy. It calculates vehicle speed, control monitor torque based on throttle input, and supports regenerative braking to recover energy duration deceleration. Uh, the controller estimates the battery state of charge SOC using Coulomb counting and predicts the remaining driving range. It also offers different driving modes such as Eco, Normal, and Sports to balance efficiency and performance according to the driving conditions. By continuously processing sensors data and making real-time decisions, the EV controller improves safety, energy efficiency, battery life, and the overall driving experience. So thank you everyone. This was all from my side.
Hello everyone, this is Gaurav speaking. This is the code that we have generated for our project. As we can see here, we have included all the header files, and here we have initialized all the functions. Now what we'll do is we will save this code and click on the build. As you can see that there are no errors or warning, means our code is correct. And now we'll go to Pixim Lab. So now here in the Pixim Lab we will go to modules, then to spare parts. Here, as we can see, these are the ultrasonic sensor for front distance, left distance, right distance. This is the potentiometer for acceleration, brake pedal, SOC, and temperature. These are the LEDs, and this is the receiver buzzer. Sorry. This is the output terminal, as we can click here and see the output of. Now, after this, we have opened command prompt as an administrator. Here we will do like this. Enter. Now we'll search the location of our file where we have placed the Python file. Enter. Now here we will search for. Here we will enter the code like this: Python space ev dashboard dot py. Now port com1 and press enter. This is the dashboard that we have created. As you can see, its speed, battery, and the here a dashboard view is also there. Front distance, left distance, and right distance. EV metrics such as torque, acceleration, brake, motor temperature, alarm, fault signal. Also in this speed history are being displayed as a graph. As we can see, here speed is 60 and battery is 95.8%. As the speed increases, the battery decreases. Now let us reduce the front distance to below 170 centimeter. Uh, as we can see here, the red light has glown up. Now let's see this on the dashboard. So here on the dashboard, it's blinking warning. The front distance is below 170 centimeter, and also the alarm shown here is critical, means advising us to stop the vehicle to increase the distance again. Now let us reduce it. Let's increase it back to above 170 centimeter and see if it become normal again or not. See, as the red light is turning off. See, it's turned off. Now let's see on the dashboard. Here also it will turn to normal as the distance increases again.